And I think we are ready to roll. I am Amanda Miller. I'm the Associate Director for the National Consortium for Data Science, also known as NCDS. We offer learning opportunities designed to address a variety of data literacy issues. And we are eager to learn more about where the needs exist, the topics that should be addressed in this space, and we seek to provide paths to increase data literacy and digital inclusion. It is my great pleasure to welcome you to the reboot of our DataBytes webinar series. We are grateful that Danielle Szafir accepted our invitation to speak this month. Dr. Szafir is an assistant professor in the Department of Computer Science at the University of North Carolina at Chapel Hill, and she directs the UNC CU Visual Lab. Her research sits at the intersection of information visualization, data science, computer graphics, and cognitive science. Before we begin, we do have just a couple of quick housekeeping items for today's webinar. I do ask that you hold your questions. Danielle will be inviting some feedback via the Zoom chat feature, and she'll get to that in just a few minutes during her presentation. But around 12:45, we will share a link to Easy Retro, which is our Q&A platform, along with instructions in the Zoom chat and on the screen so you can ask questions, share resources and comments. But for the majority of her presentation, we do ask that folks just use the Zoom chat feature and hold all questions for the audience until the end when we offer our Easy Retro board. I'll also add that if we don't get to your question, we will do our very best to address it in our wrap-up materials. And after we complete our Q&A, it's going to be my pleasure to invite you to register for an upcoming Data Matters short course series via datamatters.org. But we'll get to all that in just a little bit. Without further delay, it is my pleasure to welcome Dr. Danielle Szafir. Thanks, Danielle.
Great. Thank you all so much for having me. And thank you so much, Amanda, for the invitation. I'm really looking forward to talking with everyone today about some of the basic mechanics of how do we think about the ways visualizations might mislead and how might we overcome those? Why are they a challenge and what can we do about it? So we know that visualizations, broadly speaking, are awesome. Okay, granted, I'm biased, but in my opinion, they're a pretty great way of communicating complex information, but they can also do really bad things if they're designed poorly. Sometimes this is intentional, but more often than not, designers may not know that the choices they're making, because many of these things are very common practice, can actually lead to false conclusions by their readers. So today what I'm going to do is I'm going to talk about some common mishaps in visualization design, why they can cause people to incorrectly read data, and also some ideas around how to fix them. So before I get started, I just wanted to give you just a little bit of background of who I am and kind of the perspective that I'm coming from. So as Amanda mentioned, I direct the Visual Lab at UNC Computer Science, and we focus on a range of topics in data visualization, aiming to provide everyone from scientists to humanists to everyday people with the means for readily exploring data using our sense of sight and our own intuitions. So my research in particular is interested in how we can leverage the brain's ability to make sense of visual information to design novel visualization tools for interactive exploratory data analysis. To put this a little more simply, we just strive to make data analysis better by understanding and predicting how people work with data. So with a fantastic team of students and collaborators, we work with stakeholders to help analysts in domains ranging from literary scholarship to biology to emergency response make sense of their data and to try to guide more effective and efficient data exploration and decision making. So part of why visualization is so powerful is that it takes advantage of the brain's innate abilities to make sense of the world. I want to illustrate this with a quick example. So here I have first order statistics for 4 data sets. Would you all say these 4 distributions are quite similar? Just kind of take a minute to think about it. Looking at these, many of you have probably guessed that I am messing with you a little bit here. So all of these data sets have the same first order statistics, but When I visualize the data, they have qualitatively very different structures, and we can see that immediately here. We have linear trends, constants with outliers, and parabolic structures. We have words to describe this data and how it behaves, and we qualitatively understand the differences, even if we can't readily enumerate them. And so a lot of visualization research seeks to understand how we can leverage this ability to really see these qualitative structures and make sense of these qualitative differences in data. A good chunk of it is trying to just figure out what's the most effective way to represent data that takes advantage of these mechanisms. And through this work, we run a range of different experiments or try to taxonomize practices that designers use to come up with rules that, in general, look something like this. Then we publish our work, celebrate a new paper, and all the difference it'll make in the world. But meanwhile, months later, we turn on the TV, open a newspaper, peek in the latest issue of Science or Nature, and we see everyone is still doing Y, the thing that we told them not to do. So I've gotten in many arguments with folks in the past who insist that Y, whatever it may be, is the best way to show their data, and they aren't subject to the biases that the rest of us mere mortals see. Well, when the data doesn't convince them, we often go back to the lab and try to answer a new question, which is thinking about this idea of why should we use X instead of Y? What about the ways we see and interpret visualized data might make Y a bad choice? So going back to our motivating example, we can take a peek at these two scatter plots here to try and look at this broader process and how do we answer this question of why. So this kind of all will start with the continuum. On the left over here, we have our two charts. The process of interpreting those charts happens over time. And then so we start kind of with our sense of sight. Light from the red points, the orange points goes out of the monitor into the eye, fires off a set of signals that start the process of interpreting this information. Time passes. At the other end of this, we have insights, the knowledge that's generated using these visualizations. So insight in this case might look something like, while their statistics are the same, one of these data sets is pretty much linear. We have this constant plus an outlier structure, while the other is quadratic. We have this nice arcing curve. So what happens in between? The critical bits that lead to a visualization communicating either the right or the wrong information happen in this fuzzy gray space in between. And so by understanding the perceptual and cognitive processes between sight and insight, we can start to understand the ways we visualize data and how those ways determine the knowledge that people are able to build from data. So a few years ago, this became the motivation behind putting together the article that today's talk is based on. And if you want to go ahead and read the article, it is freely available online. But what I'm going to be focusing on today is how we can deconstruct poor visualization choices and motivate why that choice may not be as popular or natural that actively leads to better data communication. So we want to understand what's the bad practice, why is it bad, and how do we do it better? So let's take this chart as an example. I'm sure many of us have seen articles or papers arguing that our method is so much better than theirs using a chart like this. And at a glance, this chart seems to back up that story. It tells us that our method is roughly twice as good as the other. So good, in fact, that it's nearly perfect. Then we take a closer look and see that there might be something deeper going on with this chart. As it turns out, there's a lot here potentially going on. We have several elements of this chart that make it difficult to read and give us the appearance of a more dramatic or a specific difference between these methods that maybe isn't exactly there in reality. For the sake of this talk, I'm not going to tell you what those elements are yet, but if we look at a redesign of this same chart, assuming the redesign actually was come up, there it is. Okay, using more honest practices, we get a vastly different conclusion in our chart on the right. Now, I want to be very clear. I don't think the folks who design charts like what we see on the left are always, or even are often, intentionally using bad design choices to try to mislead. But to the reader, there's a drastic difference in the story that these two charts will tell using the same data. So, from here, what I want to do is I want to go ahead and introduce some ground rules for effective data visualization that call out common pitfalls that potentially mislead that you probably have seen in a lot of data communication in the past. And I want to give you alternative practices that will enable us to kind of overcome some of these challenges. So as a warning in advance, I'm going to ask for some viewer participation here. What we're going to do is we're going to roll through a series of real charts. And what I'm going to ask is, if you figure out what's potentially misleading in the chart, drop that in the chat. And then we'll go through these charts one by one and deconstruct what is the misleading bit, why is it misleading, and what can we do better? My apologies in advance that many of these examples are political. Political visualizations are often the most biased because people are using these visualizations to make a point and to persuade. So there is no political affiliation or intention behind this talk, but we will see a number of political charts. And as one final caveat before we get going, we know this talk promised 5 ways that visualizations might mislead, but you're going to get a bonus today, and we're going to talk about 6 core rules of thumb. So with that said, I want to dive in with a quick warm-up that's going to give you a sense of how we're going to work through this next section of the talk. So here I have a visualization about data from the 2012 presidential run. And what I'd like you to do is, once you see what might potentially be misleading here, go ahead and drop that in the chat. Exactly. So y'all are spot on with this one. 70 plus 63 plus 60 does not equal 100. So this is unfortunately an example that is real. This was not constructed out of false data. This is from the media. But what we can see is pie charts in general should always sum to 100. And Roxy, I agree. I don't think these things look proportional either. It looks like it's a third, a third, a third with numbers tossed on the top. But what we see here, again, the general bias we're seeing, numbers in a pie chart should always sum to 100. We can't have more than a whole. So that's going to be our first warm-up. That's kind of how this activity rolls. There's some other great observations that are coming in as we're going through the activity here. And one thing you will find is there are potentially other questionable practices that come up in some of these visualizations. So feel free to keep dropping ideas in as we go. So here is going to be our next chart. So this is a bar chart that is simply about agreements. So feel free, once you figure out what's potentially misleading here, go ahead and drop it in the chat. Yep, exactly. So y'all are getting it here. This particular chart looks on its surface like, okay, we've got a stack bar chart. It's roughly half no, half yes. But then if I uncover the title, it might also cue folks to what's going on if you haven't seen it yet. Is truncating the y-axis misleading? Here, what we have is that 99.5% of the time people actually say yes, and 0.5% of the time people say no. And so the key issue here is that we get this skewed visual proportion. What we see when we don't look at the axes is roughly 50-50 split, 2 uniform geometries. But if we look at the axes, we see that that's not at all what's going on in this data. And the sad fact is most people look at the values before they look at the axes. So this is kind of a facetious example, but this kind of thing does come up in practice. So here is an article from Business Week back in 2014 that's intended to communicate the idea that law school enrollments are absolutely tanking. And what you can see is that there is a strong downward trend here at the very end of the graph, but I am guessing that both in 1974, there were a non-zero number of lawyers in classrooms, and in 2013, there were also a non-zero number of lawyers in classrooms. And actually, if we turn around and we look at this chart in a more honest way, so this is a reconstruction on the right, what we can see is that once we pull off that broken axis and we scale accordingly, we still see a pretty dramatic dip here in our y-axis values as we get towards 2012, 2013, but maybe the situation isn't quite as dire as one might think. And this kind of case has also come up in the legal sphere. So these are charts many of you may recognize from an infamous Purdue pharma case talking about OxyContin. And the argument here with this chart, especially this chart over here on the left, is that OxyContin stayed in patients' blood levels over time so that there wouldn't be this drop off which would cause withdrawal symptoms. Well, if we look at this scale on the left, it starts at 1, which is a ratio of 10 in reality. And it's also using a log scale, which people don't necessarily have a great intuitive method of interpreting. So here, by scaling the data in a way that arguably didn't need to be scaled, we're communicating a fundamentally different idea at a glance than what's really happening in the data. And there were other data in that same report that had things like what we see in these two charts on the right, where there's actually even no units and no values and no labels whatsoever on the y-axis. So again, this idea of a misleading y-axis, people tend to just pay attention to the shape of the curve, the relative differences. They don't necessarily look to the axes and contextualize the axes, especially when they're first exploring the data. So one caveat here is that not all data has differences that are really easy to communicate, right? Many times we might find ourselves tempted to truncate the y-axis because it will let us see small but important differences between groups in our data. So for example, here I have this scale of brand favorability, and maybe some of these smaller differences are significant. They're things that I want to care about and I want to communicate. But if I have my full axis, just based on the nature of the data distribution, that doesn't come across. What I would encourage you to do if you find yourself in this kind of position is to think more deeply about the idea of what is it exactly that you are trying to communicate. So try to consider your measures. And maybe if what I care about is communicating the differences between brands, I can instead explicitly show what those differences are. So here, by showing the computed differences between brands, I have not used a misleading axis, and I'm more directly allowing that explicit comparison of differences that I wanted to show in the first place. So the takeaway here is that all y-axes should typically start at 0. Right, our next chart is an argument that Planned Parenthood service balances are changing, that since 2006, abortions are up, preventative services are down. This is a chart that was used in a congressional hearing by an advocacy organization. So I'd like everyone to take a few minutes, figure out what might be potentially misleading here. Yep, Melissa's got it here. The y-axis scales here are dramatically different. This is what we would call an inconsistent visual frame. So we have this argument that there is this change in services, but when people look at a chart like this, they assume a consistent visual frame. They assume that the y-axes are going to share the same scales. But, and I apologize if folks are having a little trouble reading some of the specific values on this chart, what we can see is on the left here, we have 289,000 on the bottom and about 2 million on the top. Whereas on the right, we have 327,000 on the top and 395,000 on the bottom. Well, last I checked, 395,000 was still bigger than 327,000. So we get this switch in visual frame. We have these two values that are being plotted on different axes, but put in the same visual space. So if we take this chart and we just simply put these two lines on the same axes, what we see is something like the data that we see here. So here we have our preventative screenings in blue, abortions in red, and we can see that there is a slight increase and a slight decrease corresponding to what we see in the chart. But there isn't this very salient, very attention-grabbing inflection point where the two values are crossing. That does not exist in this data. Another thing, too, that you might see is these lines are actually not straight lines, that there are variations in value as you go. So we're seeing also more of the data coming through. So what this tells us is we need to think about what is the intuitive frame with which a viewer approaches the data. If I see two data sets on the same set of axes, I generally expect that those axes are going to be scaled accordingly. And we've seen this more recently also in charts like this from the Georgia Department of Public Health, where what we have here is we have a series of stubborn PowerPoint slides. There we go. What we have here is a series of case counts from COVID-19. And what this looks like at a glance is that cases are going down, that they're steadily decreasing over time. But if we actually look at the x-axis here, we can see that we have April 28th, 27th, then we jump up to the 29th, May 1st. So we're moving all over in time. There's no linearity to the temporal scale here on the x-axis. But if people see time, they expect time to move in a singular linear progression. So by changing this up, the intention was, can we compare different case counts over high count weeks or lower count weeks? But in reality, what it does is it creates this false illusion of cases going down over time. So the takeaway here is that we should keep our axes consistent. We should know what people expect to see and will intuitively expect when they look at a graph, when they think about the units of the data, and make sure that things are scaled and ordered appropriately. All right, so our next graph is a little bit of an oldie but a goodie. This is a figure from the 1970s about campaign expenditures over time. So take a few minutes, think about what might be misleading here and drop it in the chat. It's not the x-axis, but that's a good guess. That probably isn't helping anything if I'm being honest. Okay, we're going to take about 30 more seconds. All right, so we don't quite have it here, but the core thing that's actually misleading here doesn't have anything to do with the data. Okay, arguably tilting the x-axis probably doesn't exactly make it easier to read. But what we have is this monster that all of the data is occurring in, right? We're actually presenting the data in the context of a rhetorical frame. And while it seems like this shouldn't be a big deal, we see things like this all the time. This is an instance of what Edward Tufte calls chart junk. Visual information that doesn't really support the data, but instead pushes a specific interpretation of the data. And in particular, this can introduce a kind of cognitive bias, a shift in the way that people are actually reading and interpreting the data that's introduced by this rhetorical cue of having the values in the mouth of a monster. So the visual imagery that we see here actually has the power to persuade us towards a certain expectation of the data. And this can actually be as simple as just using a title like monstrous costs, right? We're trained to think that these values are bad and then we should have some explicit interpretation of it. In theory, your data should be interesting enough that presenting the information in a straightforward and arguably somewhat boring chart like this should be sufficient to get across your point. And you can always jazz it up with a little extra graphic design and whatnot, but this extra embellishment can actually affect people's interpretation of the data, how they remember that data, and the conclusions that they draw. So for example, it turns out that this bias is fairly robust overall. So there was a study done in 2018 by Kong et al. That looked at biases introduced by title alone. So this is not adding any extra visual embellishment like we saw with the monster. And what they did is they showed people charts like this, where we would see defense budget on a steady decrease as percentage of GDP, even though the values are going up, or a defense budget on an increase in constant dollars, even though the values are going down. So even when we had titles that were actually running counter to what was shown in the data, people would recall what was seen in the titles more so than they would what was in the data. And ironically enough, having the data and the title conflict with one another didn't make the data seem any less trustworthy or any less reliable. So we have this almost mismatch between the interpretation presented by the designer and what's actually going on under the hood with the data. So one caveat I want to throw out there is that this kind of charging, this kind of visual embellishment might actually support cognitive accessibility. So in some past work that we did in our lab, what we actually found is that But being able to carefully design semantic cues, kind of semantic basic icons that support people in understanding what the underlying data is about, we can actually make the data more accessible for people with intellectual and developmental disabilities. So we get this kind of trade-off in making the data more accessible versus thinking about the rhetoric that we might be introducing through the addition of this chart junk. But a good takeaway here as a general rule of thumb is, when possible, scrap the chart junk. Think about how the rhetorical frame in which the data is being presented might affect the interpretation of the data itself. All right, so I am sure you have all seen a million charts like this. Here we have 3 approaches. We looked at the runtime of different algorithms over time, and we're presenting the aggregated information from those runtimes. However, there is one key issue here. Once you've spotted it, go ahead and drop it in the chat. And Patricia, if you could send me an email, I'd be happy to pass that article along. The color is a good guess, but that's not the biggest issue going on here. Yep, Elizabeth's got it. We don't necessarily know what the actual values are here. What we're doing is we're presenting an aggregate picture of the data, but in presenting that aggregate picture, we're simplifying this complex data process down into 2 values. And granted, sometimes we actually have to do that. But what we might be doing is hiding vast differences in our data distributions. So representations like a violin plot that we see here on the right actually show a lot more information about the distribution to help with more effective sense making. For example, it can reveal skews in the data or biases or outliers that, just averaging and presenting some error bars doesn't necessarily help. So if we see the same data presented as it is on the left versus on the right, we're going to draw 2 very different conclusions about what's going on in this data. And there's actually a really interesting study done in 2014 by Carell and Gleicher, where they showed people different visual representations. They had, for example, a bar chart with error bars like we just saw, violin plots, something called a gradient plot, where you essentially faded out the color values from the means, or your traditional box and whisker plot. And what they found was that these kinds of representations that show more information about a distribution, not only do they provide additional data for reasoning, they actually led to lower decision biases when it came to understanding whether samples are more or less likely to come from particular distributions, and to comparing those distributions overall and drawing effective conclusions about the magnitude of differences between different samples. Caveat here is we've all seen charts like this where more data is not always a good thing. There is such a thing as too much data. And so there are processes that we can use, and I'm not going to go into detail about, but there are a number of different techniques that are available for doing what we call aggregation or summarization. So there are ways of computing and aggregating and blending together the data and designing our visualization to show those aggregate values in ways that support different kinds of decision making, depending on the needs of your problem and of your audience. But the key takeaway for all of this is you want to try and show as much data as is necessary for people to make effective decisions. Aggregating things together into statistics might simplify that decision-making process, but not always in desirable ways. So this chart is a chart from a presentation that was done at Apple looking at US smartphone market shares. And I'd like you to take a few minutes, and once you've figured out what's going on here, go ahead and drop it in the chat. Yep, exactly. So you all are on to it. So here we can look at this and say, wait a minute, since when is 19 and a half bigger than 21? What we have here is an issue of 3D distortion. This pie chart, typically speaking, when we want to highlight values, we want to emphasize values, those values would be on top. But if what we're doing is we're ticking out the bottom of the pie chart, 3D perspective says things that are closer to us are larger. So what we've done is we've essentially moved the center of this pie up, and we make things on the bottom look larger than things on the top. I still contend one of the best things Microsoft could do for effective decision-making is remove the ability to make 3D pie charts from PowerPoints. So what we're doing here is we're distorting the perceived area of different values in the pie charts. So what we could do is we could think about something as simple as take the same 3D pie, make it 2D, one way to fix it. One of the other things that we might want to think about is, well, if what we're trying to do is do a direct comparison, it's good for some things, but if we're just trying to compare areas, it's a lot easier to compare the length of a bar than it is the area of a wedge. So depending on how precisely we want to try to communicate these messages, even changing up the representation can be helpful. And granted, 3D pie charts are a problem. And I think it's a fairly well understood element of visualization that 3D pies aren't necessarily our friends, but we still see visualizations like this all the time where we have 3 variables and therefore we make a 3D chart with 1 variable on each axis. But Brian is spot on here. People are not great at comparing volumes or areas. They are not great at doing this kind of mental 3D projection onto a 2D space. So we run into issues here like occlusion or perspective. We aren't necessarily very good at mapping the height of any of these bars onto any of these axes. And in fact, it's really, really hard to see what is going on in those bars in the back corner. And so what we can do is think about, are there ways to move away from 3D and show this higher dimensional data more effectively? We could do something like take the exact same data and apologies for the tech issues today. There we go. We can map it onto things like size or color. Where here we take the same grid cells that we have here in this 3D chart, but instead of mapping to the height and trying to project that height onto the back axis, what we're doing is we're instead comparing the size or the color of these values to make a more immediate and more perceptually refined and precise comparison. So as with the other roles, one caveat for this is when you actually have spatial data. So for example, this was a system that we built a while ago, where we were looking at binding site predictions on protein molecules. So the basic idea here is that there are chemical properties and spatial properties, geometric properties about the surface of a protein that cause it to bind onto different molecules like DNA. So if we need the spatial data and we need this abstract chemical or electrostatic charge data, what we can do is we can provide tools and techniques that allow us to navigate the molecule in 3D space to see the data embedded in the physical space. One of the things that we do, though, when we think about representations like this is think about what are the tasks we need to address. So if I need to, for example, compare lots of these molecules, it might be worth thinking about what are the trade-offs of unfolding these molecules or temporarily removing the spatial information to allow for rapid comparisons. Because, for example, I can't see half of this molecule at any given time. So spatial data can sometimes require 3D, but I would say in general, avoiding 3D is a really good idea for effective data communication. All right, we've got one more for you here. So this is a map that was taken from a paper where they were looking at precipitation loss over different counties in the continental US. So once you see it, go ahead and drop it in the chat. All right, I think you all have got it here. This is a problem with the rainbow. So the rainbow color scale is incredibly popular, but it can also be incredibly misleading. So here, if we look at this particular scale, we see this really hard line dividing right down the middle of the country. And actually, the difference in this hard line in the middle of the country is the same as the difference between this blue and this green here in Ohio. There is a very subtle shift in one case and a drastic shift in the other. And what is going on here? Well, we can look at this particular representation, and we've got two major problems. So one is the steps between colors in this graph are just straight up not the same. So if I look at this particular set of colors, I have this step from the magenta to the purple being equivalent to that from the purple to the blue. And those three differences are also supposed to be equivalent to the three differences between this blue, this kind of blue-green, and this green, right? These three differences, there's no way we're going to necessarily see them as the same. And one of the things our brain does is even in a more carefully designed rainbow color map, something like JET or Turbo or some of the others you might have seen in other tools that you've worked with, rainbows also tend to group colors together. Our brain likes to simplify the problem. So we tend to look at groups of similar colors like reds and yellows and oranges as being more like to one another than groups of another color. So we might have a yellow that is equidistant to a green, but it also tends to appear as if it is more like other yellows that might be further away. Micklin also brings up a great point here that color blindness is a huge issue here, right? We have massive accessibility issues in many rainbow color schemes. So I have gotten into more arguments than I probably should have with people about rainbows. And one of the studies that showed that rainbows can be really rough, even for people who are used to working with them, was done in 2011 by a group of researchers at Harvard. And they were working with doctors where they originally had visualizations of epithelial shear stress. So think about this as measures of blood flowing through arteries that look like what we see in C here. They were these 3D molecules with rainbow color maps on the top. And what they needed to be able to do, the doctors needed to be able to do, is rapidly find areas of high epithelial shear stress. And so this group of visualization researchers came in and they said, hey, we know from past experience, rainbows aren't great, 3D isn't great. Let me give you something that looks like what we see in part B here. And the doctors were generally on board with the idea of getting rid of 3D, but there was a harsh pushback on getting rid of the rainbow. It was comfortable, it was familiar. They had this confidence in their ability to use the rainbow. So what the researchers did is they said, okay, we have this history of thinking rainbows aren't effective, and maybe in this case you are used to using them. Maybe it'll work out. Maybe everything will be good, and we can just keep the rainbow. So what they did is they ran a region detection task where they asked people to make diagnoses using these images that were colored using different color maps. So here we have our classic rainbow in A and a range of other choices drawn from visualization tools on these other examples. And to cut to the chase, what they found was that when you shifted from a rainbow, which is shown here in the center light bar, to a black to white to red, so this kind of diverging color scale, which is shown here in this dark gray bar, we got a spike in diagnoses from 62% to 91%. So this is one case where avoiding the rainbow could actually save lives. And we also see this huge jump in performance when we move from 3D to 2D. So this is some additional information saying that rainbows, while they're pretty, they're engaging, they're familiar, might not always be so great. And so part of this is because, like we talked about, rainbows can create these bins, these artificial divisions in our data. If we look at this heat map here, we have the same data presented using a rainbow versus using just what's called a sequential scale, where we go light to dark. And we see these hard, crisp boundaries around different color groups, from blue to cyan to green to orange to red. Those color groups may have absolutely nothing to do with what's going on in the data. There might be smooth gradations like we can see here in the sequential map, but they appear as if they're firm boundaries because of the way our brain wants to group light colors together. There also tends to be no intuitive ordering. If we go back to that original map we looked at the start of this, that map kind of mixed colors all around, and it didn't necessarily look like there was any disorder in the rainbow. So we have this kind of artificial mixing of the colors in ways that could cause us to mix up our values and see highs as lows and lows as highs. So the general fix here is you want to try and match the data to the data type, or sorry, match the color encoding to the data type that you're working with. If I have continuous data, I'm probably going to want a sequential color scheme somewhat like this. One caveat here is that rainbows might actually be good for something in our continuous data distribution. So we ran a study a few years ago, and we actually have a paper that we just learned yesterday is going to be coming out. So I apologize, I don't have it here, but I'm happy to send it to people offline. But that basically suggests the rainbow might actually be good for some things. In particular, those kinds of tasks that people need to do, where simplifying the data mentally is a shortcut that will help you reason about complex data. So what we did is we ran a study where we simply would show people groups of 4 data sets like this, and we'd ask them what data set comes from a different distribution. And we used a whole range of color maps, everything from our classic turbo over here to the left, which is a variant of the rainbow color map that is designed to be a little bit more accessible and a little bit better perceptually because they kind of tweak the lightness properties of the map, versus what traditional visualization tells us should be optimal, something like this set of blues over here on the right. And what we found when we looked at this comparison task across a range of these color maps is that rainbows were actually really, really good at helping people find the oddball in a data distribution. We had no intentional alignment between the data and the color map. It was just straight up values you see in the data or values you see in the color map. And we found that rainbows and other kinds of representations that had this color name variation, that had lots of different nameable colors like reds, yellows, blues, greens, tended to perform really well at this task. So what this means, we're still figuring out. For the most part, I would say a good rule of thumb is to try to avoid the rainbow, but there is a growing body of literature that suggests the rainbow might be useful in some cases. So those are the rules of thumb that I wanted to walk us through today. Just to recap, our y-axis should start at 0. Try to avoid truncation. If you need to truncate, think about changing the units on your graph. Keep your axes consistent. People have an expectation about what a visual frame of reference will look like for a given data set. Try to design to that frame. Scrap chart junk. Visual imagery and embellishment can cause all sorts of rhetorical issues that can bias people's perception and memory of the data. Show the necessary information. Simple is good, but not when it hides the things that people need to know to make effective decisions. Avoid unnecessary 3D. 3D perspective can distort the ways that our data is presented in ways that lead to false conclusions. And beware of rainbows. Rainbows in general are probably not going to be your best bet, both in terms of the accessibility issues that were raised in the chat, but also because they do funny things to the ways that we reason and compare about data. There are a ton of other guidelines out there for effective data communication. A few resources that I want to call out here are things like VizGuides. VizGuides is a community forum of researchers and practitioners where you can go ahead and raise questions about best practices and get a good discussion and lots of pointers to references and whatnot from the community about effective data representation. If you're up for keeping up with some of the most exciting and new stuff coming out in the field of visualization, Multiple Views is a blog platform that attempts to take the research that's coming out in all these conferences and journals and turn it into something actionable and accessible for people who want to work with their data using the most recent best practice. There also is, I have a Coursera course available that goes over a lot of the foundations of visualization. And I believe, I apologize, I should have asked Amanda about this beforehand, but I believe there is also an upcoming DataBytes course on data visualization that should be a lot of fun. So there's lots of resources out there. I'm happy to point folks to more. You can also go ahead and just send me a note. Always happy to sync up. Amanda, do you want to throw something in there?
Yeah, thank you so much. We will be adding, if you could just pop to the next couple slides, Danielle.
Yeah.
We're going to be sharing some information about Data Matters, which is the, oh, sorry, just go back one.
Okay.
Yeah, thank you. Yeah, we'll be adding some information about Data Matters in just a minute, but now is the really fun time where we take a moment and invite you guys to submit questions on our Easy Retro board. I'm going to go ahead and ask my colleague, either Jay Shri or Savannah. Thank you so much. It looks like someone has dropped that Q&A platform into the chat bar. I am going to copy these instructions. So it's really easy to add the plus sign onto the relevant column. Danielle, if you wouldn't mind passing, let's see, we are going to pass the screen to me so I can share our DataBytes Easy Retro board.
Good.
Yeah.
Sounds good. And while I'm passing that over, feel free to reach out at any time. My email is available on my website, I think, as part of the talk announcement. But feel free to reach out at any time. Also, if you want to chat, if you have any questions, you want to follow up on anything, always happy to set up a time for a good conversation.
Excellent. Thanks so much. So folks, I have the DataBytes screen for Easy Retro up on the board right now. If you guys just want to go in and add your questions by entering an item here about building effective visualizations, you can add a question here, common pitfalls in visualizations. Feel free to just type something in. How do we avoid pitfalls? And then you can save those. And then you can easily upvote or comment on your colleagues' ideas, questions, and resources. So feel free to add in anything that's appropriate and relevant to the webinar at this time. It looks like we've got one comment from, let's see, no need to add your names, by the way. It looks like we have a comment. Danielle, can you see the screen?
I can, yep.
Okay, great.
Sorry.
Oh, so here we are. We've got a couple folks coming in. If you want to just go ahead and repeat the question as you are answering it, that would be great.
Yeah, so it looks like one of the questions is about building effective visualizations, thinking about never using broken axes, except maybe in scatter plots. I would say in general, trying to avoid broken axes, even in scatter plots, is important. The one place that becomes really tricky with that is if you're thinking about things like clustering, for example. So if what you care about in your visualization has nothing to do with the raw values that are going on. So for example, I have a scatter plot, I just want to show clusters. I don't necessarily care about the absolute scale. Let's say you're using something like principal component analysis, so arguably units don't even matter anyway. Then thinking about times that it might be okay to break the axes are very reasonable. Another thing that we often do, and I'm guessing whoever wrote this was paying close attention here on the slides with the color maps. But another thing we'll often do is we'll actually scale axes to chance if that is a meaningful benchmark. But one thing I would say is, whenever we do that, we also try to call out in captions that, hey, we scaled this, but we scaled it for this reason. Because at a glance, again, our brain is not going to process the text right away. It's going to process the relationships it sees. So if the relationships we see at a glance are the things we need to communicate, then we can maybe sometimes be a little more lenient on these. That's why these are all rules of thumb. There are definitely times to break them, but definitely think about what might be communicated by changing your axes or by following any of these practices. Bubble plots, great question. So what are your thoughts on bubble plots? Bubble plots are beautiful graphs that are often used in really weird ways. So for folks who are familiar, what a bubble plot is, it's basically a scatter plot plus size, where you vary the size of the point according to a given data dimension. So when we're varying the size of those points, one thing to be careful of is that the points are varied according to area rather than diameter or radius. If we order according to we change the size according to diameter or radius, it's easy to implement, but it actually distorts the perceived differences in value because essentially we're squaring the differences. So our values are changing by the square rather than by the actual size. That being said, bubble charts have other effects. So for example, one of my PhD students was able to model the fact that we get this attentional bias where we perceive the average of a group of points as in a different spot, moving towards the larger points. So when we have a bubble chart, we're actually we're skewing people's attention and we're causing people to estimate statistical values that more heavily weight the larger points in our graph over the smaller points. There are cases where this might be all right, but many cases it's probably not. And I have no idea what order these all came in at, so my apologies here. Right. I'm jumping ahead. One idea for pie chart, yep, I would definitely agree with you there. Multi-part figures are interesting. So the question here is just like, what's the thought about multi-part figures? Sometimes phenomena, and this gets to that, one idea per chart kind of thing. Sometimes phenomena are very complex and they're best illustrated across multiple charts. And in fact, we have concepts in visualization that talk about this idea of what's called brushing and linking. So if I interact with one chart, I see changes in a corresponding chart. What I would say is if you're trying to communicate ideas across multiple charts, people are notoriously terrible at being able to intuitively build associations between different representations. If you want to see some fun illusions, go ahead and look on YouTube for things like change blindness. So if you are going to communicate data across multiple charts, one thing I would definitely encourage you to do is A, keep that consistent visual frame, keep your colors mapped to the same idea, keep your axes scaled accordingly whenever possible. But B, try to, whenever possible, also use design cues that help people track the important information from chart to chart. This might be as simple as always highlighting the same data points, or it might be as complicated as finding ways to explicitly connect and link between charts. So multi-part figures are often necessary for communicating complex phenomena, but think about how you can support the cognitive needs of your user as you move across charts. And to that last one, The Building Effective Visualizations, yes, that is a fabulous book for folks who haven't read it. Storytelling with data. There are a lot of great references out there. That one in particular, I think, is really well tuned to people who just want to build things and really want to know what those best practices are in an accessible way. So another question here is, how do we train people, be they youth who might be learning to use visualizations for the first time or adults who already have experience with using and creating and thinking critically about visualizations? I think this is a fantastic question. Visualization literacy is really, really challenging. One of the things that's really interesting is we've been starting to do some work with kids and building toolkits for kids to learn about data literacy. So in particular, we've got a project with the National Science Foundation and some folks in tangible computing back at the University of Colorado, where what we're trying to do is build these kind of construct your own toolkits that leverage a cell phone, some mirrors, and construction paper to let kids build what are called interactive physicalizations, so physical representations of data. And so by kind of playing and constructing with these physicalizations, what we found is that kids start to see data as a creative and playful medium, something that's interesting and expressive. And our hope is that we can use this to try to shortcut negative attitudes about data that emerge earlier on. But there's a lot of cool information out there about visualization literacy and thinking about what are the best practices for teaching people to read and work with and critically interpret charts. I think we have a whole lot of work to do because the ways data are being used is far outpacing our knowledge of how to teach people how to use it effectively and how to interpret it effectively. But my hope is that as we start building out these resources, that there's going to be some really cool opportunities to advance. So there was a special issue last year, I think, of computer graphics and applications that had a number of really cool articles around visualization literacy. There's some work being done. In particular, the groups that come to mind are Samuel Huron's group out of INRIA in France and Sheila Carpendale out of Calgary. They've done some really cool and really innovative work with thinking about how do we teach people about data? So there's lots of great resources out there that are still, unfortunately, predominantly in the research realm, but increasingly we're seeing more and more motion and activity towards making visual literacy and visualization literacy a more common and accessible thing that we teach in both in the classroom and outside.
I think that's really helpful. And we will, if you don't mind, Danielle, sharing those resources with us.
Happy to.
Yeah, that'd be great. We can send that information out to all of you in our wrap-up materials for this event. So in the interest of time, I'm going to give us some space for one more question. I don't know who that lucky person's going to be. A lot of gratitude coming in the chat box. So again, really, thank you so much. Once again, this was an amazing presentation. It looks like Rachel Kaplan has raised their hand. Go ahead, Rachel.
Sorry, I just wanted to say this is more of a Captain Obvious kind of statement, but it was great, like the framing of this as here are the pitfalls, here what you want to avoid. And my mind cynically goes to the, how to. These are things that I should do when I want to manipulate my audience and get them. So I was just wanting to hear your comment on the other side of the cynical side of this.
That's totally fair. It's completely a double-edged sword. And that's one of the things I think we don't necessarily have great techniques yet for being able to call out. There is a motion in the community towards moving towards things like visualization linters. But this is fairly similar for folks who are more in the programming space. This is very similar to like a linter you'd have for code that's going to call out when best practices are being used or when they're being abused. And so this kind of motion towards, can we start to detect when some of these things are happening? Can we flag them? Can we even potentially retarget our visualizations in ways that fix them is something people are looking into. Right now, I think our best tool is education, is, helping people understand when things can go wrong and how we might go about fixing them. But it's definitely a huge problem, right? This is kind of that chicken and egg problem of, if we understand what we're doing and we understand where things go awry, can we use those in nefarious ways? There's some really interesting writing by Michael Corral talking about black hat visualization that also gets into this problem of what happens when we know what can mislead and people decide to use that for nefarious purposes. I would hopefully assume that's not what's happening in these examples, but.
Thank you. This was so fun.
Thank you.
I'm so glad you enjoyed it. So thanks so much, folks. Do feel free to continue to use this as a space for Q&A. This will not end with our webinar. And we will be checking this to craft some follow-up points, as I mentioned earlier. So we will follow up with Danielle to get some of those items she mentioned and share those out with all of you. So I'm just going to return us to our little welcome and let you guys know how incredibly honored we are that you chose to spend an hour with us today. We just ask that you do shoot us an email to let us know if you are interested in becoming a DataBytes speaker. We would love to have you join us, and we hope you guys all have a great rest of your day. Take care. Bye-bye.